Big sigma refers to writing a large capital Greek letter sigma like this. And in math, that means we're going to add a bunch of things up. So that is what a sigma looks like. And that's the capital letter. The lowercase letter sigma looks like this, but that's not super important. Lowercase sigma is a symbol we use in statistics for the standard deviation of a random variable. But capital sigma means we're going to add a bunch of things up. When I write something like this, like n equals 0 or n equals 1 or something below, this is what we call the index variable. And then there's going to be, with the index variable, a lower bound. And then up on top, there's going to be something like another number called the upper bound. And then right here, in front of the sigma, this is called the sum end. And the sum end kind of tells you what every term is going to look like. So underneath exercise 1, you can see an example of this. Has anybody seen this before in any context? Physics? Okay. One other place you see this is in statistics. In stats, we'll have like some list of measurements, like x1, x2, x3, x4, and so on. And if you want to know what is the mean, the sample mean, or the average of this list of measurements, what you would need to do is you would need to take a sum where your index goes from 1 to n, the sample size, and then you would divide that by the sample size. This is the formula for the average, or the formula for the sample mean from statistics. But we use a capital Greek letter sigma to tell you, hey, all of those measurements, we are adding those all up together. We're adding them up. Okay, so whenever you see something like this in exercise 1, the way I read it is like I'm adding up a bunch of terms that look like k, where k is going to go from 1 to 6. So in other words, this sum is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6. Mm-hmm.
So what's the difference between this and like 6 factorial?
6 factorial would be 1 times 2 times 3 times 4 times 5 times 6. So this is going to be 21, I think, when you're done adding that up. If I have something that looks like this, so I've got the big sigma, I'm going to add up a bunch of terms. My index variable k is going to go from 3 to 5, and my sum end is k squared. So all of the terms are going to be starting with 3 squared plus 4 squared plus 5 squared which is going to be, of course, 9 plus 16 plus 25, which is 50. So let me pause and make sure. Does everybody feel like you understand what's going on here? Okay. Now, I've got a challenge for you. Who can tell me what this sum is? You could get in your calculator and type in 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. It might take you a really, really, really long time, though. Can you think of a faster way to think about this? The funny thing is, when I was a little, kid watching like Saturday morning cartoons, we didn't have Netflix, we didn't have cable, we didn't have streaming, right? It was just like you tuned in the TV to the channel you wanted to watch on broadcast TV. And as they were broadcasting the shows, they would broadcast commercials, and in between the commercial breaks, or right before the commercial break, they would interrupt your cartoon with like a riddle or a puzzle so that you'd have something to think about and do during the commercial break, and then after the commercials were over, they would tell you the answer. And so I remember this vividly as being like one of the puzzles before a commercial break on Saturday morning while I was watching my cartoons. But does anybody have any ideas for what that's going to end up being? And take a guess. Okay. Nobody gets a prize then. No free t-shirts this morning. Okay, so what this looks like is 1 plus 2 plus 3 plus ... Plus, eventually we'll get to 97, 98, 99, 100. And in between here, there's also going to be a 50. Maybe I'll make a special point of indicating where the 50 is. But it looks like that. And so the way they explain this to us during my Saturday morning cartoons is that, well, you could pair up 1 and 99, and you could pair up 2 and 98, and you could pair up 3 and 97. And the reason I want to pair these up is because they add together to give me 100. And so each one of these orange pairs is 100 times how many little orange pairs are there? 49. And then I also have to remember the 50, and I also have to remember the 100. So I've got 4,900 plus 100 plus 50, and so the answer is 5,050. But I thought that was a neat little puzzle, worth mentioning while we're talking about the big sigma notation. And in general, if you want to solve this problem for any upper bound to n, there's a formula for it. And these are called the triangular numbers. And let me explain why you might call these the triangular numbers. It's going to be a matter of like calculating a particular area. Let me just tell you that the area of this square is 1. And so the area of this rectangle is 2. And the area of this rectangle is 3. Okay, and so imagine we keep doing this for a while. We make as many rectangles as we want. And then after some time, we reach our top rectangle, and it has area n. I don't know what n is. But who knows? There's some number of rectangles in between 3 and n, where n is just our upper bound that we're counting to. And so if I could just calculate the area of all of these rectangles, then I would get my answer. I just need to find a way to calculate all of these areas together. And so the trick here is to say, well, what if I complete this square here? Because there's n rectangles, and the tallest rectangle has a height of n. And so this square has this side length, n, and this side length, n, right? So for my orange area, that's going to be n squared. Of course, that's bigger than the area of the rectangles, but the next trick that I want to use is I want to draw a diagonal line down through the tops of my rectangles. And so obviously everything below this green line is part of the area of the rectangles. It's not the total area. There's some little peaks that stick out above the green line, but everything below the green line is going to be part of the rectangles. And so the area below this green line is a triangle. It's n squared divided by 2. So how do I capture the areas that are here that are just peeking up a little bit above the green line? How do I get the areas of these triangles? Well, each triangle has an area of 1/2. And how many triangles are there? Well, there's n triangles, right? Because there's however many rectangles you want in the middle there, right? Because n could be the number 15, n could be the number 35. So however many rectangles you want, however many triangles you want there in the middle. But there's going to end up being n triangles, each with an area of 1/2. So if I just add together n squared over 2 plus n over 2, that's going to give me the area of all the rectangles. And that's going to be my answer. And so what you see here in this theorem is just another way of saying n squared plus n divided by 2. Because if I take n squared plus n divided by 2 and I factor out an n, then voila, that's my formula. So now instead of having to use 99 operations in your calculator while you slowly add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 and so on, this only requires 1, 2, 3 operations. Right? Start with n, add 1, multiply by n, divide by 2. It's a really good shortcut. So I bring this up because I want to teach you something called induction. We haven't learned induction yet, but I'm about to show you a proof by induction. You know already what we're doing this unit in the book is just a bunch of lessons about proofs. How do we prove, for example, the derivatives that we talked about last time, the derivative rules. Proof by induction is a technique that goes like this. I'm going to first prove that it's true in the base case where n is equal to 1. And then the next thing I'm going to prove is if it's true for an arbitrary case n, then it must also be true for the next case, n plus 1. And so you can imagine this like dominoes. Whenever you set up a proof by induction, the fact that a particular statement, a particular claim is true for n equals 1 will imply that it has to be true for n equals 2, and that implies that it has to be true for n equals 3, and that implies that it has to be true for n equals 4, and that implies that it has to be true for n equals 5, and so on. We call this induction because it covers the rest of the positive integers by this inductive argument. So the mental image of like dominoes comes in handy. We'll come back to this, but I want to show you the same theorem, but this is going to be a proof by induction. And the proof by induction works like this. We say, consider when n equals 1. Well, when n is equal to 1, the left-hand side of this equation is going to be a sum that includes only one term where the term looks like the number 1. And that's the left side of my theorem. On the right side, I've got 1 times 1 plus 1 divided by 2, which is 2 divided by 2, which is 1 on the right side. And so we have verified that this theorem works for the case when n equals 1. Okay. Now we are going to assume that this is true. For any arbitrary n, we're going to go ahead and make the assumption that this formula works. Okay, I know we haven't proved that yet, but for now, just enter in the world where we're assuming that this is true. And then we need to prove that this formula is also going to work for the next case. And the next case is the case where n is now n plus 1. So again, this is the way that induction works. Because if I could just prove this, that anytime this formula is true, then this formula is true, right? Anytime it works for the n case, it works for the n plus 1 case. Well then, I just have to show that it works for the n equals 1 case, and that implies it works for the n equals 2 case, and that implies that it works for the n equals 3 case, and that implies that it works for the n equals 4 case, and all the dominoes fall. So that's what we want.
How did it turn into n plus 1, n plus 2?
Because we just replaced n with n plus 1. Does that make sense? Everywhere I saw an n, I replaced it with n plus 1. So this n plus 1 becomes n plus 2. Yeah. So this is like what we're assuming, and this is what we have to prove for the next case to be true as well.
Oh, because that would be inside the parentheses would be n plus 1 plus 1. So you just did n plus 2.
Yes,
Okay.
exactly. All right. So consider we've got the sum from k equals 1 to n plus 1 of k. This is going to be equal to the sum, where k goes from 1 to n of k, plus n plus 1. Now, by our assumption, I can replace this big sigma that goes from k to n with n times n plus 1 divided by 2 plus n plus 1, right? And then I'm adding with a fraction, so I need to find a common denominator. What it would look like to find a common denominator is like this. So I've got n times n plus 1 plus 2 times n plus 1 divided by 2. And then in the numerator, I've got two terms that I'm adding together that have the same factor, the same n plus 1 factor. So let me just factor out the n plus 1. And what it looks like to factor out the n plus 1 is n plus 1 times
2. N plus 2.
n plus 2. What we needed to prove is that this sum that goes up to n plus 1 is equal to n plus 1 times n plus 2 divided by 2. And what we just showed is that this sum that goes from k equals 1 to n plus 1 is, if we just rearrange it a little bit, equal to n plus 1 times n plus 2 divided by 2. So we just proved that if we assume this is true in the first place, then it has to also be true in the next case. And since we showed that it works in the case where n equals 1, that implies that it works in the case where n equals 2, that implies that it works in the case where n equals 3, and so on and so on and so on. It works for all of the positive integers. So this is called a proof by induction. And I want to introduce this because we're going to use this in other places too. This is not the last time you're going to see an argument by induction to prove something. But do you have any questions about what we just did?
So which part is like the act of induction? So induction only correlates to when we have the sigma? Or like, can we use it for other?
You can use it for other things too. It doesn't have to be just about theorems involving the sigma. The part that's induction is saying, I'm going to assume that it's true and then prove that it's true for the next case.
Okay, so that's induction.
That's the induction idea. Okay. So switching gears a little bit. Suppose you're a traveling salesman and you need to drive to 5 different cities this week to meet clients. If you're responsible for making your own schedule, you can put these 5 cities in any order that you like. How many different ways can you put 5 cities in order? So your schedule looks like this. You've got to visit 1 city first, and then 1 city second, and 1 city third, and 1 city fourth, and 1 city fifth. And how many different ways can you put 5 different cities in order?
$15?
15? Why do you say 15?
I just did the n times n plus 1 over 2.
Oh, no, it's not that.
Oh,
Hmm? What did you say, sorry?
24.
24. How did you come up with 24?
It'd be 5 different cities, so you have to put them in 5 different ways. So then it'd be 25, but it's used to track 1. There's 25. So 25.
That's not it, but I'm glad we're thinking about the problem a little bit. Hudson?
It's 25, isn't it?
25?
Yeah.
No.
Oh,
Okay. How many different choices do we have when we plan out our first city we're going to visit? 5 choices. Yeah. I've got 5 choices for whatever city I'm going to choose first. Then let's say I lock that in. I write that down on my paper. I've chosen the first city I'm going to visit. How many choices do I have for choosing the next city, the second city? 4 choices. And I lock that in. I'm going to write down that choice on paper. How many choices do I have left to choose for the third city? Yeah, there's only 3 cities left. And so when I'm visiting my third city, I've only got 3 choices left. And then finally, whenever I get down to my last city that I'm going to visit, there's only 1 city left on the list. I've got only 1 option here. And so this is like already locked in, basically. I don't have really a decision in front of me to make. Does that help? So what's the number of ways I can put 5 different cities in order? 120. Because I've got 5 times 4 times 3 times 2 times 1 different ways to do this. Because every time I have a decision, I'm multiplying by the number of choices I have when I make that decision.
so in this case, we could just do 5 factorial.
Exactly. This is 5 factorial. Yeah, it's 5. Okay. Yeah, so y'all jumped the gun on me, but this is called a permutation. Whenever you have a set that has different elements, and I'm asking you how many different ways can you put the elements of a set in order, that would be a permutation. And the factorial is a function that's defined for positive integers that is just decreasing, multiplying from that number, right? So 5 factorial was 5 times 4 times 3 times 2 times 1. Of course, you don't have to multiply by 1 if you don't want to, but you can.
So like if there was a question, like there's 1,000 different cities, could you just put 1,000 factorial?
1,000
for the
factorial.
answer?
Yep.
Okay. But there's no other way.
Factorials grow really fast, by the way.
There's no other way to like actually get the answer, or like from like a big number. You know what I'm saying? Other than typing it in your calculator and doing it.
Right. Well, even your calculator is not going to do a factorial that big. This is a really interesting discussion, but it would take too much class time to go into it. But I'll tell you a few things. A deck of playing cards has how many cards in the deck? 52. So if I were to shuffle the deck of playing cards and mix them up, how many different orders could I potentially rearrange the deck into? 52 factorial, right? Because there's 52 choices for the first card, 51 choices for the second card, and so on. So there's 52 factorial ways to shuffle a deck of playing cards. 52 factorial is a number that is so big. 52 factorial is larger than the number of atoms in the observable universe. And that's just 52. So 1,000 factorial is obviously bigger than that. You know, these are really, really large numbers. It grows really quickly. So yeah, 52 factorial is giant. When we talk about computers and what your calculator can do, you should be aware that like computers all have a finite size, right? Like even if you have a really big computer, it's limited to the amount of space it can take up. This one's, you know, maybe 1.5 feet by 1.5 feet by 5 inches tall. And that means there's only a finite amount of information you can store in a computer. So whenever you store numbers in a computer, you have to choose the way you're going to represent the number on physical memory, like the ones and the zeros, and how do you represent ones and zeros with transistors and so on. You've got to make a decision about how you're going to do that with physical memory. And the numbers that we can do on a computer probably include 50 factorial. Yeah, that's a big number, but it can still be stored. But I don't think it includes 100 factorial. Oh, wow, I'm actually surprised. What about 1,000 factorial? No, it doesn't. Okay, so when this happens, your computer is saying, listen, the way we chose to store numbers as a string of ones and zeros on physical memory in the transistors, that kind of convention doesn't allow for numbers this big. Because you can't choose to store every number. There's infinitely many numbers. You can't choose a data type convention that's going to allow you to store every number, or your computer has to be the infinitely large computer. Another kind of interesting consequence of this is, what if I type in 1.005 minus 1? What do you think the answer is going to be? 0.005, right? Okay, it looks like that might be true on the surface. Let's give me some more digits of accuracy. And my answer is 0.0049999999999999999999999. Obviously, it's not true, right? But the reason for this, the reason why Excel gets this wrong, is because the number 0.005 is not a number that can be stored in computer memory. You have to select what real numbers you're willing to represent on your computer memory with ones and zeros and your physical transistors. And you can't store them all, right? Even between the number 0 and the number 1, there's infinitely many real numbers. You can't choose to store infinitely many numbers. You've got to select which ones you're going to pick. And so this one didn't make the cut. Instead, we can store this number in physical memory. And so what Excel does after it does the calculation is it chooses the closest representable number in computer memory. And it happens to be this one. So you get a small round off error here. If you are interested in learning more about this, Google search IEEE double precision floating point, and there's a Wikipedia page for it. But it'll tell you how do computers use zeros and ones to store approximations of real numbers. And it's kind of an interesting topic. But this is the reason anybody says, like, oh yeah, even computers have round off error. It's because of stuff like this. You can't store every real number in a computer. Okay, so regardless, with factorial, since they grow really fast, you can't store like 1,000 factorial in a computer anyways. So you could write your answer as 1,000 factorial. Okay, you're judging a chili cook-off and there's 10 competitors. You have to rank all 10 chilies on your scorecard before turning it in. How many different ways can you put 10 chilies in order? And the answer is 10 factorial. Yeah. 10 times 9 times 8 times 6 times 7 times 5 times 4 times 3 times 2. New example. Your toddler is playing with blocks. There are 5 unique blocks: red, blue, green, orange, and purple. Your toddler's tiny hands can only hold 2 blocks at a time. How many different ways can your toddler choose 2 out of the 5 blocks to hold? This is a thinker. Don't just tell me 5 factorial. It's not right.
5 factorial over 3 factorial.
You're close. I've got 2 hands, so I can do this experiment myself. So I pick these 2. That's 1 possible choice. 2 possible choices. 3 possible choices. 4 possible choices. And then I move my hand over to the blue because I've already exhausted all the red ones. 5, 6, 7, 8, 9, 10. 10 possible ways to do this. And this is where all the stat students always ask me, is it just 5 times 2? And 10 is 5 times 2, but that's a coincidence. That's not the right formula. Okay. Yeah.
Wait, so what if you do mathematically there to figure that out? Or do you just have to think about it in your head?
No, there's a way. I'll tell you.
Oh, okay.
Consider another one because let's say you go to compete in a golf tournament. There's 12 golfers. They're dividing the golfers into groups of 4. The first group of 4 is selected at random. How many different ways can you choose 4 out of 12 golfers? So this is a problem where I'm not going to be able to just use my hands and think about it, right? Choosing 4 out of 12, that's a lot. That's a lot of choices. I'm not going to be able to just logically think through this. I mean, well, let me rephrase that. I'm going to need to logically think through this because I'm not going to just be able to wave my hands and count, right? So here's what I suggest. We've got 12 golfers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's put the 12 golfers in order. And remember, that's going to be 12 factorial different ways to do that. Then take the first 4. Which means I'm going to draw like a partition here between the first 4 golfers and the last 8 golfers. And then recall that we don't care about the order of the first 4. Or the last 8 for that matter. Because whenever I have 12 factorial ways of putting 12 golfers in order, that's going to give me a bunch of situations where I have the same first 4 golfers, but I've just permuted the first 4 golfers. Like they just show up in a different order, but it's still the same first 4. And I don't care to know the difference between those cases. And the same thing is like, I'll have a bunch of cases where I have the same last 8 golfers, and the last 8 golfers are in a whole bunch of different orders. But I don't care what order they're in, right? I only care which 4 get selected. So when we go to do this, we are going to take 12 factorial for the number of ways to order the golfers. Then we're going to divide by 4 factorial. And then we're going to divide by 8 factorial. Because there's 4 factorial different ways to permute the first 4 golfers, and I don't want to distinguish between those cases. As long as they're the same 4, I don't care how they're lined up. Likewise, there's 8 factorial different ways to permute the last 8 golfers, and I don't want to distinguish between those cases as long as they're the same last 8. So we have to divide by both of those numbers to remove the duplicates. And the only significantly different ways to do this are going to be 12 factorial divided by 4 factorial divided by 8 factorial. So I'm going to have 12 times 11 times 10 times 9 times 8 factorial divided by 4 factorial times 8 factorial. Do you understand why 12 factorial is the same as 12 times 11 times 10 times 9 times 8 factorial? Okay, and then you see how there's an 8 factorial in the numerator and an 8 factorial in the denominator? So those guys just cancel. That's nice. So in your calculator, all you have to type in is 12 times 11 times 10 times 9 divided by 4 times 3 times 2. And 12 divided by 4 is 3. 10 divided by 2 is 5, and 9 divided by 3 is 3. So you could even really just do this in your head if you want to, which is 9 times 5 is 45. 45 times 11 is that 495? Of course, on a test, just use your calculator. You don't want to take any chances there, but... Turns out there's 495 ways to choose the first 4 golfers in a group out of 12 possible golfers. So we call this a combination. A combination of a set is whenever I take a subset of its elements in no particular order. Like if I've got 12 golfers and I take 4 golfers, that's a combination of golfers. I took 4 of them, I took a subset, and I didn't care what order I was taking. Whenever we do the math, we call the math part the binomial coefficient. And this is what it looks like. Notice this is not a fraction, so don't write n divided by k. But the binomial coefficient is written like this. N is the size of the set, and k is the size of the subset. So like n is 12 golfers, and k is 4 golfers in the starting group. When you see this on paper and you want to read it out loud to somebody, you would say, n choose k equals n factorial divided by k factorial divided by n minus k factorial. Right? So what I mean is, you see this symbol, you see the binomial coefficient. When mathematicians read this out loud, you say n choose k. Or 12 choose 4.
So for like the block question, it would be 5 factorial over 2 factorial.
Yeah, we can double check and make sure it works, right?
5 minus.
This is 5 choose 2, which is 5 factorial over 2 factorial, and also over 5 minus 2 factorial. So it's like 5 times 4 times 3 factorial over 2 times 3 factorial, which is 10. You're eating at Genghis Grill. There are 8 types of protein. Only 3 can go into your wok bowl. How many different ways can you choose 3 out of the 8 proteins? Well, 8 choose 3 is 8 factorial over 3 factorial times 8 minus 3 factorial. So that's 8 times 7 times 6 times 5 factorial over 3 times 2 times 5 factorial. The factorials are going to cancel each other. 8 divided by 2 is 4. 6 divided by 3 is 2. 8 times 7 is 56. You got 56 different choices when it comes to proteins at Genghis Grill. This is kind of fun, right? A little bit different than typical calculus class. A little bit of a change of pace. So this is called Pascal's rule. It's a theorem about binomial coefficients. And it says n choose k plus n choose k minus 1 is equal to n plus 1 choose k. And the proof is pretty boring, but the proof just follows from a little bit of algebra. What we're going to show is that n choose k plus n choose k minus 1 is equal to n factorial divided by k factorial times n minus k factorial plus n factorial divided by k minus 1 factorial times n minus k minus 1 factorial. Okay, well, let me factor out an n factorial from the whole thing. And then I'm going to think really carefully about this. I notice over here, yeah, let me not do anything yet. I'm going to take it slow. Sometimes I like to rush ahead and do a whole bunch of steps all at once, but then again, maybe it's better to just do one step at a time. Like when I have n minus k minus 1, that's the same thing as n plus 1 minus k, because you distribute the minus sign and 2 negatives make a positive on the 1. Now I'm adding 2 fractions, and anytime I'm adding 2 fractions, I want to find a common denominator, right? So in the next step, my goal is to find a common denominator. And that means for the first fraction, I need to make it so that I don't know. I like the k factorial but I want the n minus k factorial to be n plus 1 minus k factorial, which means that means in the numerator I need to include a little n plus 1 minus k factor. And then on the second fraction, I like the n plus 1 minus k factorial. I just want to turn the k minus 1 factorial into a k factorial so that it can have a common denominator with the other fraction. And to do that, I need a k in the numerator. So this is probably the hardest step in the proof. So let's pause for a moment and just accept that when I have a k factorial in the denominator and a k in the numerator, that would simplify to having just k minus 1 factorial in the denominator, right? Because the k's cancel, but what's left of this factorial will start with k minus 1, and then times k minus 2, then times k minus 3, then times k minus 4, and so it'll be the same as k minus 1 factorial. And the same thing is happening here. If I have n plus 1 minus k factorial, oh, I put the factorial in the wrong spot. That's bad. Bad, bad, bad. There we go. If I have n plus 1 minus k factorial, that's the same thing as n plus 1 minus k times n minus k factorial. So by putting this in the numerator, it makes it equivalent to just having the n minus k factorial in the denominator. Taking the first factor from those factorials and putting them in the numerator so they can cancel each other out. And that gives me a common denominator, so I can finally add these fractions. And when I go to add these fractions, of course, they have the same denominator as intended. And the numerator gets to be n plus 1 minus k plus k. In other words, n plus 1. Now, n factorial times n plus 1 is the same thing as n plus 1 factorial. And do you see how this is n plus 1 choose k? Because I've got n plus 1 factorial divided by k factorial and n plus 1 minus k factorial. So that's the binomial coefficient for n plus 1 choose k. And that's exactly what we were trying to prove, right? We were trying to prove that this expression is really equal to this expression. We just wrote down the proof for Pascal's rule. Is there any step in this proof that you want to talk about? Anything you don't understand here?
Where'd the factorial go in the last step? Because there's like 3 of them there.
Where did the factorial go in the last step?
Factorial over k factorial, and then it just goes to n plus 1 over k.
Oh, this isn't n plus 1 over k. This is n plus 1 choose k. So remember, you can see right here, n choose k, by definition, is n factorial divided by k factorial times n minus k factorial. That's the definition of n choose k. And so all we're doing when I say n plus 1 choose k is I'm taking this formula, but I'm replacing the n's with n plus 1's.
So it wasn't a simplification to get the answer. It just matches what we.
Yeah, if I were to sit down one day and say, I want exactly the formula for n plus 1 choose k, what I would write down is n plus 1 factorial divided by k factorial times n plus 1 minus k factorial. That's, by definition what it means to be a binomial coefficient. So good question. Good question, because I think a lot of people were thinking the same thing. A lot of people had the same question, which is good. So what I'm trying to build up to in this lecture, the title of your homework says the binomial theorem, is this. What I eventually want to explain to you is why does this formula have to be true? And this formula is saying we've got x plus y in parentheses raised to the power n and notice there's some stuff going on. I've got the big sigma notation, so it tells me I'm going to be adding up a lot of terms. All of the terms are going to look like n choose k, my binomial coefficient, times x to the k times y to the power n minus k. So if I want to expand the polynomial x plus y cube, the way I'm going to do it is just kind of follow this binomial theorem formula. This is going to be the sum as k goes from 0 to 3. And every term in the sum is going to look like 3 choose k times x to the power k times y to the power 3 minus k. So this sum is going to have 4 terms. There's going to be a term where k equals 1, a term where k equals 2, a term where k equals 3, and a term where k equals 0. Right? So that makes 4 terms. I should have started counting with 0. A term where k equals 0, and then a term where k equals 1, 2, and 3. So let's write those out. When k is equal to 0, this is 3 choose 0, x to the 0, y to the power 3 minus 0. I add to that when k is equal to 1, and I add to that when k is equal to 2, I'm going to add to that when k is equal to 3. How many ways can I choose 0 out of 3? 1. X to the power 0 is 1. 3 minus 0 is 3. Then how many ways can I choose 1 out of 3? 3. And then x to the power 1 is x. And then that's y to the power 3 minus 1. How many ways can I choose 2 out of 3? 3. And you'll notice choosing 2 out of 3 is the same thing as picking 1 out of 3 not to choose. So in other words, it has to be the same as 3 choose 1. But then I've got this. How many ways can I choose 3 out of 3? There's only one way to do that. Y to the power 3 minus 3 is y to the power 0. Anyways, we can simplify and simplify and simplify. I get y to the third plus 3xy squared plus 3x squared y plus x cubed.
So, sorry, you said how you got the 3 and the 0, how'd you get 1?
This is saying 3 choose 1, which is saying how many different ways can you choose 0 items out of a 3 item set? If you've got 3 blocks, how many ways can you choose 0 blocks? If you've got 3 blocks, how many ways can you choose 1 block or 2 block or 3 blocks? Yeah. And you can check this against the traditional way of doing things. Like you may have had to do this in like a college algebra course where you just take x plus y cubed and call it x plus y times x plus y times x plus y. And then if you do this one at a time, like maybe combine these two, this would be FOIL, right? First, inner, outer, last. And then you've got to FOIL this thing, which is going to give me like, I don't know, x cubed. And then x times 2xy is going to give me 2x squared y, plus this x squared y is going to give me 3x squared y. And then y times 2xy is going to be 2xy squared, plus this xy squared gives me 3xy squared. And then, of course, y cubed. So you get the same answer either way, whether you want to do it the old way or whether or not you want to use the binomial theorem. Because, and hopefully I can kind of convince you of this, is that when I say 3 choose 0, what I'm talking about is like, what I'm talking about is like, I've got 3 appearances of the variable x, and I'm not going to choose any of them. I'm going to choose 0 x's, and instead I'm going to choose all y's. Boom, boom, boom. When I choose 3 y's, I get the y cube. And right here, whenever I have 3 choose 1, I'm talking about how many different ways could I choose one of these x's. Well, I could choose this x, and this y, and this y. Or I could choose this x, and this y, and this y. Or I could choose this third x, and this y, and this y. And those are all the different ways where I can get 1 x and 2 y's. And then where I have 3 choose 2, I'm talking about how many different ways can I choose 2 x's. Like I could choose this x, and this x, and this y. Or I could choose this x, and this x, and this y. Or I could choose this x, and this x, and this y. But in any case, that's 3 ways to choose 2 x's and 1 y. So there's 3 ways to choose 2 x's and 1 y. And then lastly, here, I'm talking about how many ways can I choose 3 out of the 3 x's. Of course, there's only one way to get 3 x's, 1, 2, 3. And that's how many ways I can get x cubed. So hopefully the picture of foiling and using the binomial coefficient looks the same. We talked about the big sigma notation for being able to calculate the sums of things that have multiple terms. And then we talked about the triangular numbers. And you saw kind of a geometric picture proof of the triangular numbers. And then we also gave another proof by induction for the triangular numbers. And you don't have to prove things twice, but I wanted to show you and demonstrate how induction works, how that line of reasoning works. How induction is saying, like, we're going to set up the base case and make sure the base case is verified. And then we assume what we're trying to prove, and then prove that the same formula works for the next case. So we switch all of the n's to n plus 1s, and then we prove the next case works. And if the base case works and the next case works, well, then the next case works, well, then the next case works, and it goes on and on and on, kind of like the picture of falling dominoes. We talked about permutations and how to count the number of ways that you can rearrange a set. We talked about the binomial coefficient and combinations and the ways you can count how many different ways to choose a subset of elements out of a set. And we proved Pascal's rule, which was really just a lot of algebra that involved factorials and finding a common denominator and adding fractions and all that kind of thing. And then we did an example using the binomial theorem. And let's do another example using the binomial theorem. And then we'll jump to the proof here. But this says, expand the following polynomial. If I have x plus 1 to the 4th power, then I can use the binomial theorem where n is going to be equal to 4 Since n is equal to 4, I'm going to go ahead and just plug that in here. 4, 4, 4. If you need a reminder, this is what the binomial theorem looks like. And I've just replaced the n's with 4's. So all told, there's going to be 5 different terms here. And what is the y this time? I changed the y to a 1. Oh, sorry, that shouldn't be a 4, that should be a k. I must have written down my binomial theorem, so let me try that again. X to the k times 1 to the power 4 minus k. But 1 to the 0 power is 1. 1 squared is 1. 1 cubed is 1. 1 to the 4th power is 1. So I don't need to bother multiplying by 1. And like I said, there's going to be 5 total terms. The first one is going to be 4 choose 0, x to the 0, and then 4 choose 1, x to the 1, and then 4 choose 2, x to the 2, and 4 choose 3, x to the 3, and then 4 choose 4, x to the 4. So how many ways are there to choose 0 elements out of a set with 4 total? 1. Yeah, 4 choose 0 is 1. X to the 0 power is also 1. What about, how many different ways are there for me to choose 1 item out of 4? 4 different ways. How many ways can I choose 2 items out of 4?
2.
Yeah, Well, if it's not obvious, you can just use the formula, which is like 4 factorial divided by 2 factorial times 4 minus 2 factorial. And then how many different ways can I choose 3 out of 4? And how many different ways can I choose 4 out of 4? So let me rewrite this polynomial as x to the 4th plus 4x cubed plus 6. Is that 6? It was like 4 times 3 divided by 2. So 6. And again, to check your work, to make sure you did the binomial theorem correct, you could do it the old-fashioned way, where you write x plus 1 times x plus 1 times x plus 1 times x plus 1 and think about foiling. But it would just maybe take longer. I don't know. There's some point where this becomes faster and easier than just using the old-fashioned college algebra way. But that's how you do it. That's what the binomial theorem says. We talked a little bit about how you could kind of argue for and justify the binomial theorem as a matter of choosing the x's or choosing the y's out of the ones you're available to FOIL. But what we were about to do yesterday is prove the binomial theorem by induction. And so you start off by considering the base case where we set n is equal to 1. And if I set n is equal to 1, this is really easy to verify because this sum, where the big sigma is, has 2 terms. One term where k is equal to 0 and the other term where k is equal to 1. And the term where k is equal to 0 is going to give me a y, and the term where k is equal to 1 is going to give me an x. And so it works out just fine. And then the induction part is we assume exactly what we're trying to prove, right? We assume that this is true. And what we have to prove next is that if it works for the case when n is equal to n, let's prove that it will have to work when we change that to n plus 1. That if it works for one case, it has to work for the next case. That's the goal. So we take this, we look at the left side, and we're going to expand it. So instead of having the n plus 1 power, we've got the n power, but we also multiply by an extra x plus y. Does that make sense? Okay, what's happening in this next step? What's happening here? Yeah, we are assuming that this is true. And so what happens in this step is we're going to use our assumption. By replacing the x plus y to the n power with this sum. And that's why it shows up here.
Oh, okay.
So you're taking one, you're looking outside, and then you're choosing
Yeah.
Okay. So then, Avery, what's happening in this green step? How do I go from this line to this line?
I think they did like the big sigma for the first x plus y.
Mm-hmm.
So now there's 2.
Well, not exactly. I'm not replacing the x plus y by a big sigma thing. What is happening here is I'm distributing. I'm distributing this whole sum into the x plus y. so that whenever I distribute this to the x, now I have x to the power k plus 1 instead of just x to the power k, because I'm multiplying by an x. And then when I distribute this to the y, I'm going to get y to the power n minus k plus 1 instead of just n minus k, because I'm multiplying by an extra y. So this is what it looks like to use the distributive property. All right, Carter, what's happening here in this next step? Here in purple. This is a really hard one. I'm not. I'll give you the answer because this is.
Each side to be equal? Are you like trying to make each side equal to each other?
Yeah, that's a really good insight. So, what I'm doing in this purple step is notice the second sum is staying exactly the same as it was before. No changes to the second one. But for the first one, there's something really, really, really subtle happening.
Is it Pascal's rule?
No, it's not.
Or like induction?
It's not Pascal's rule yet. We are eventually going to use Pascal's rule, but not right now.
You're getting the n plus 1 and then you have the plus n.
What we're doing in this next step is I'm changing it so that for this sum in particular, this one only, we are replacing k with k minus 1 everywhere where that occurs. So k is my index variable, and so you can do kind of sneaky things with it like this. It's very, very, very subtle. But notice in this sum, the one I'm pointing at right now, the first term that appears would have k equal to 0, right? And when k is equal to 0, this would be n choose 0 times x to the power 1 times y to the power n. Well, this sum is exactly the same. I know it says that k is starting at 1, but I would still have n choose 0 as the first coefficient. I would still have x to the 1 power, and I would still have y to the n power. Because I replaced every instance of k with k minus 1. Like here there's a k, here there's a k minus 1. Here there's a k plus 1. Here there's just a k, because it's k minus 1 plus 1, yeah. And then here there's n minus k. I'm going to replace that with n minus k minus 1. Then I know to change the k equals 0 to a k equals 1, because if I were to set k minus 1 equal to 0 and then rearrange, add a 1 to both sides, I get k equals 1. So that's why I'm starting now at k equals 1. And then instead of just ending at n, I also need to bump that up into n plus 1 so that I can keep the same number of terms in my big summation. So that's a really, really difficult step to wrap your head around, but that's what's happening. I'm keeping exactly the same sum, but I'm just shifting the index so it looks slightly different. Okay. For the next one, let's see. Kyle, can you tell me what's happening in this blue step?
You're just distributing and rearranging the terms above the y.
Exactly. Yep. If you just look at the powers of y, I'm distributing the minus sign so that it says n plus 1 minus k, and I'm also making this power of y look like n plus 1 minus k, because I just want the powers to look the same. And so we are adjusting the powers of y. All right, Rhett. Tell me what's happening when I go from here to here. This is another one that's kind of a challenge to understand, but what's happening in the orange step?
Expanding it somehow.
Yeah, that's okay. Because like I said, this is a tough one to wrap your head around. Notice the first sum is exactly the same, except for what? Yeah, I took this down from n plus 1 just to plain old n. And so that means there's a n plus 1 term missing. I'm missing the term now where k is equal to n plus 1. So I'm missing the term where you have n choose n plus 1 minus 1, or n choose n. And I'm missing, then the same term would have x to the power n plus 1 and y to the power 0. And so what I've done is then I added that last term here out to the side, because I don't want to change the value of what I'm doing. Instead, I'm just taking that last n plus 1 term out of the sum and putting it right here, writing it down more explicitly. Okay? Then what happens to the last sum? The index used to start at 0. Now it starts at 1. So it's exactly the same sum, except for this one is missing a term. And the term that it's missing is the term where k is equal to 0. And so I went ahead and I wrote that term of the sum out to the side. So you get the k equals 0 term here, and then the rest of the sum right here. So in other words, this is the same thing as this, and this is the same thing as this. The reason why I'm trying to do this, why would I bother, is because I want the indices to match on the sums. In other words, here they don't match because this one's k equals 1, n plus 1. This one's k equals 0, n. I want them to match. So I want k equals 1, k equals 1, n, n. And now the sums have matching indices, and they have matching powers of x, and they have matching powers of y. I'm trying to get those two sums to look the same, so that way they play well together. I wish there wasn't like such a big page break here. But what's happening in the next step is this term shows up over here, unchanged. This term shows up over here, unchanged. And I bet Carter can tell me. Carter, what's happening here in purple?
Is that Pascal's rule?
It's Pascal's rule. Yeah. Because now that I have the same indices, and I have the same powers of x and the same powers of y, the only thing left to do is add together these coefficients. And the coefficients over here are n choose k minus 1. The coefficients over here are n choose k. And then when I combine them and I add them together, I get n plus 1 choose k. That is exactly what we proved yesterday. And it's called Pascal's rule. So go back and find that. Here's Pascal's rule. N choose k plus n choose k minus 1 equals n plus 1 choose k. That's exactly what we are invoking here in order to smash those two sums together. And that's why my new coefficient is n plus 1 choose k. But otherwise, the indices stay the same, the powers of x stay the same, the powers of y stay the same. I'm just adding those two sums. Okay. Next step. I'm including this blue term in the big sum because I'm shifting the lower bound of my index from k equals 1 to k equals 0. So it gets to include that one. Then I'm also including the green one because I'm shifting the upper bound from n to n plus 1. And so it's going to actually include this. And if that's hard to see, it's because this is actually equal to the same thing as n plus 1 choose n plus 1. If you want, because n choose n is 1, n plus 1 choose n plus 1 is 1. X to the power n plus 1, y to the power 0. Okay, and now you can probably see a little bit more easily how that gets included when I make the upper bound of my index variable n plus 1. Then I would get this. So by lowering the lower bound and raising the upper bound, I get to include the blue term and the green term, and then I get this as my final expression. So now, you can tell we've reached the end of the proof. How does this prove what we're trying to demonstrate? How would this prove the binomial theorem? Well, remember that we're doing induction. And in induction, we set up the base case where n is equal to 1. And then we assume that this is true. And if that's true, we need to prove that the n plus 1 case is true as well. In other words, the n equals 1 case is true. We just proved that the next case has to be true. So then the n equals 2 case is true. And because we proved that the next case is always true, that means the n equals 2 case is true, the n equals 3 case is true, the n equals 4 case is true, the n equals 5 case is true. And there's always a next case. And so this has to be true for all of the positive integers. That's the beauty of the induction proof technique. So one thing students always want to know is like, is this going to show up on a test? And I'll tell you this, if I'm typing out the proof in class and not just like writing it by hand, then I'm not going to just give you a question that says, prove the binomial theorem on a test. That would be a little bit unfair. So the big picture here is that writing original proofs, you know, like out of the clear blue ocean is like a hard skill for even like graduate mathematics students to like master. But we try to build students up to this so that like in undergraduate, that is like in your 4 years of college, you would typically be expected in a math class to be able to like regurgitate proofs, especially short proofs, you know, that like you've learned. You're not coming up with the proof yourself, you're just seeing it, you're understanding it, you're kind of committing it to memory so that you can recreate it on a test. But for longer proofs, we wouldn't even bother like making you regurgitate this. I'm not going to make you recreate this line for line. But there is a skill in terms of like being able to read a proof and understand a proof. We're still going to spend some lecture time reading difficult proofs and trying to understand it like we did. But I think to answer the question is though that like, if it's one of these proofs in lecture where I'm able to write it down myself, if I can just remember it, you know, like the proof of Pascal's rule, or, for example, the proof of the triangular numbers. If it's something that's relatively short like this, then yeah, I think I should be able to ask that on a test. But if it's a really, really long one where I have it typed out, like this one is actually typed out on my notes, I'm not going to make you recreate this on a test. We'll just read it together in class and we'll try to understand it, because I think that's an important skill, to be able to read and understand a proof, even if you can't memorize it.